This video explores manifold-constrained hyperconnections, or mHC, a technique for building more stable, scalable neural networks. You'll see why conventional hyperconnections struggle, how manifold constraints fix these issues, and what performance and efficiency gains become possible at large scale. Traditional hyperconnections widen residual streams and stack many paths between layers. While this can increase representational power, it also amplifies or attenuates signals unpredictably. As depth grows, gradients can vanish or explode, creating severe training instability and making models difficult to optimize reliably. A key issue is the loss of clean identity mapping. In ideal residual designs, layers can easily learn the identity function, allowing information to pass unchanged when needed. Hyperconnections often break this property, causing features to be distorted as they travel through depth, which undermines gradient flow and hampers stable learning. Because hyperconnections freely combine many streams, there is no inherent guarantee on signal magnitude. Some paths can become excessively strong while others wither away. This unbounded amplification or attenuation means small numerical imbalances compound over layers, forcing practitioners to rely on ad hoc tricks instead of principled stability guarantees. Manifold-constrained hyperconnections address these issues by projecting the connection weights onto a carefully chosen manifold. Instead of allowing arbitrary mixing, every transformation is restricted to lie in a stable region of parameter space. This preserves identity mapping when needed and keeps the overall transformation well-behaved during both forward and backward passes. Under manifold constraints, the network can smoothly interpolate between identity and more complex transformations. Signals can flow through many layers without being arbitrarily distorted, which stabilizes gradients and reduces training pathologies. As a result, deeper and wider networks become easier to train, even when they use rich hyperconnection patterns. A practical way to implement the manifold constraint is through doubly stochastic matrices, where row and column sums are controlled. This structure regularizes how information is distributed across features, preventing runaway amplification. By balancing contributions in both directions, it mitigates vanishing and exploding signals while still enabling expressive feature mixing. Manifold-constrained hyperconnections use convex combinations of features to conserve a meaningful feature mean while tightly regulating signal norms. Instead of relying solely on normalization layers, stability is baked directly into the connection structure. This provides predictable signal propagation, making optimization smoother and improving robustness to hyperparameter choices. Despite its mathematical sophistication, mHC is engineered to be efficient. Techniques like kernel fusion and selective recomputation keep the additional costs small, amounting to only a modest increase in training overhead. This allows practitioners to adopt the method in large models without sacrificing throughput or drastically expanding hardware requirements. When evaluated across scaling experiments, models equipped with manifold-constrained hyperconnections consistently outperform comparable baselines. As compute or token budgets increase, the performance gap widens rather than shrinking. This indicates that mHC not only stabilizes training, but also unlocks better use of capacity, enabling stronger models at the same computational scale. The technique challenges the assumption that dramatic gains in intelligence require exponentially more power. By removing bottlenecks created by unstable training and inefficient signal flow, mHC helps extract more capability from a given compute budget. This reframes progress in AI as a problem of smarter architectures, not just larger hardware deployments. Manifold-constrained hyperconnections transform hyperconnected neural networks from unstable curiosities into scalable, high-performance architectures. By restoring identity mapping, enforcing structured constraints, and preserving signal norms, they enable deeper, more efficient models. These ideas point toward an era where architectural innovation, rather than brute force compute, drives breakthroughs in AI capability.